So the assignment is BH and BP curves using WebPlot digitizer. Inside the assignment, there's a lot of files you have to download, and there's a link that we're going to use. Let me show it. So I'll just read what I wrote as like the assignment statement. So for this assignment, you will locate the plots of the BH and BP curves for a given material from its datasheet. Use a WebPlot digitizer to convert the BP plot image to a .tab file and ultimately import the tab file into the material properties for the given material within Ansys Maxwell 2D. So this is the link to the plot digitizer. This is the PDF of a Nippon Steel grain-oriented steel datasheet. This is the download for an empty tab file, and this will be the link to the recording of the lecture in class, which I'm recording right now. And go ahead and download this Maxwell model that we'll be working on, and it's the synchronous reluctance motor that we were working on from last lesson. And with this, we'll be able to calculate an estimate of the efficiency of the motor for a given speed and torque. And we will simulate the motor at base speed and max torque today, thus max power, and then extract the iron and copper losses to estimate the efficiency at this data point. And although this leaves out stray losses and more impactful than stray mechanical losses, we're still going to use it as an estimate. And what you're going to submit is screenshots of the core loss and the stranded loss from our simulation. So I'm going to download this model. And first, everybody go ahead and download the PDF of the datasheet and open that up. So this is the datasheet for some electrical steel, and in the model I linked in the assignment, the BH curves are already defined for the Nippon 27ZH100, and what we're going to do is we're going to get a BP curve. So that's basically a core loss model that's going to it basically models like hysteresis and eddy current losses within the steel. And you can find that in the data sheet. Let's see if we can find it together. So I'm just gonna Control F and search for 27ZH100. And yeah, so here are some curves for the 27ZH100, and this curve we already have. Oh wait, no, this is the BP curve we're extracting. This BH curve we already have imported in Ansys. So what we need to do here is we need to screenshot this BP curve, and then we're going to put it into the WebPlot digitizer. So if you know how to take a screenshot on your laptop, I'm going to zoom in a little bit. Yeah, so we're going to screenshot this iron loss curve. Take a screenshot like that. And then it's not saving. There we go. And then download your screenshot, save it wherever you'd like. Screenshot it and save it as a PNG. So now we're going to go to this link on the assignment, the web plot digitizer. And I'll wait a second for you guys to screenshot the 27ZH BP curve. Alright, so go to this link, the web plot digitizer, and if you go to File and click Load Image, then you can choose a file. And then I'm selecting the screenshot we just took. And 2D XY plot, and we're going to align the axes. So first we're going to put the points x1 and x2. We're going to click to place them, and then we're going to put y1 and y2. So you can see the zoomed in view on the right, and just select any values as long as you know what they are. So here it says 0.1, and I'm going to try to get as close as I can.
Alex, does it matter if it's a semi-log sheet and the other one?
Yeah, it'll ask later if it's log scale or not. So you can. So I'm getting as close as I can to 0.1, so that's x1. And I'm going to go to 10. And choose there. And now I'm going to do y1 and y2. I'm just going to 1 and 2. And then hit complete. And now we have to input the values. So the x-axis is log scale, so make sure on the right you check log scale. And x1 is at 0.1 and 0.2 is at 10. And then the y-axis is at y1 is at 1 Tesla and y2 is at 2 Tesla. And hit OK. And now we're just going to go along this curve. I'm going to choose the 50 Hertz curve. We'll just have to define that when we're doing the materials definition, but I'm choosing 50 Hertz curve for now. And we're just going to go along and place points along this line. So we don't need that many points, but get a relatively good amount of them. Yeah, just arbitrarily place points along the entire curve. No, just make sure it looks like it'll capture the general trend of the curve. And once you've placed a relatively good amount of points, make sure you downloaded the empty BP curve tab file. So I'm gonna download that right now, and I'm gonna go to my downloads, and I'm gonna rename it. So I'm gonna say this is Nippon Steel 27ZH100 BP curve 50 Hertz. That's what I'm renaming it. And now I'm going back to the web plot digitizer, and once you've gotten all these red dots here, you can go to view data on the left, and here's all the points we just selected. So once you have the BP empty curve downloaded, go ahead and open that, and it should be a text file. And make sure you have 0 and 0 as the first point, because Ansys won't let you create a BP curve unless it starts at 0, 0. And now we can just copy paste this data, Control C, Control V here, but you have to make sure to delete the commas in between the points. So I'm just going to go in and delete all these commas. So if you go to the file, okay, so if you download the file, if it doesn't automatically open as a text file, it might ask you. Just make sure you, oh, sorry. You download it here on the assignment. No problem. So I'm just deleting all these commas.
Guys, anybody know a shortcut to delete the commas?
Mm. Oh yeah, you could just change that to a space. Whoa! Alright. So now if you have these values, make sure you save the file. So file, save, and that's all we have to do with the webplot digitizer for now. So again, so what you do once you have these points here, again, click View Data, and you can change the column separator. It's automatically a comma. Yeah. It should be the same format as the file you just downloaded. It should be .tab. So this is what your file should look like. And now if you have this Maxwell model open, we're going to move over there now. So here's the Maxwell model, and you can see the rotor and the stator iron are Nippon Steel 27ZH100. So if you right click Nippon Steel 27ZH100 and click Properties, it'll select the material, and then you can click View/Edit Material. So right click Nippon Steel 27ZH Properties, and then View/Edit Material, and the BH curve should already be in there. And you're going to go to Core Loss Model right here, and you're going to change it from None to BP curve. And then this little button says BP curve. If you click on that, this is where we can import the data set. So then if you go to this button up here, you can click Import Dataset, and then find wherever you downloaded it. And now we need to look through the datasheet to find out what frequency. So we already know the frequency is 50 Hertz. We're going to find out the lamination thickness. So I'm going to Control F 27ZH100 again. And let's see. Oh yeah, you have to make sure in the .tab file that the first 2 points are 0, 0. Yeah, in here. Yeah, it's fine. It's just like creating a general curve. Yeah. Question.
It's saying that the x-axis here is the magnetic field and the y-axis is the power. Is that correct?
No. Yeah, we need to swap that. So let me check. It should be. Usually it already has Tesla on the y-axis. So we might have to swap the data set in the .tab file right now. Because when you input it to the BP curve in Ansys Maxwell, it puts Tesla on the x-axis and the core loss on the y-axis. Yeah. So, yeah. Let's see. I'm not sure if I can swap it in here.
If you have Notepad++, what you can do is you can just hold the Alt key and then select the right-hand data on the what would it say it would say by dragging it, then copy it, and then do tab the left-hand data and then paste it on the other side. No, in Notepad++, not Notepad.
Oh, okay. So let me just make sure.
Oh, I see. So Tesla's on the y-axis on this part.
Mhm. Yeah. So yeah, we're gonna have to go back and redo the web plot digitizer. I think you can align the axes over again. Yeah. So yeah.
Bro, you could just ChatGPT it would.
Really?
Yeah, it just tell it to flip the order of the columns and it does it for promise
Um,
this guy. Oh, that is wow. We should AI take our job.
so
Yeah, I actually
now I think the data is formatted correctly. Is it? Right. I don't think it flipped actually. Oh. Hmm.
No, okay, so that's why
Mm.
that issue of increasing on the curves. It's coming back for some reason.
Alright, I'm just gonna restart.
Put a lot of
Oops.
I can't tell. 9, 5. Oh. Oh, there's these extra points right here. That's what it is. Okay, so I'll just delete that. Oh, where's that come from? scroll down, and if it ever goes down, then that's considered to show the increasing the B value. You see how there's like 0 point, it's like some extra points for some reason. So like I would just get rid of those or something. Just like put in the data. Oh, just put in the data and then just say switch the columns and it should do that. Those work for you?
Right. Alright, I reformatted it with the X and Y axis swapped and pasted it into the file, saving it again, going back to the BP curve, and now my red lines are like kind of off, but Ansys should create the general trend for you, even if you didn't select the line perfectly. So just making sure. I believe the core loss units are in kilowatts per meter cubed. So make sure the frequency is 50 hertz. And if we look at the data sheet for 27ZH100, the lamination thickness should be 0.27 millimeters.
Alex, is it possible that we do a curve fitting and find the order of this curve?
Maybe in Excel, yeah. I think. So lamination thickness will be 0.27 millimeters. The unit, the B field unit is in Tesla. The core loss unit is in kilowatts per meter cubed. Okay. Oh, okay. Now it's mad at me because I actually input the data bed. So I should have been more precise with selecting the line. I kind of rushed it. I think it's because this point is coming backwards. Yeah. Okay. So I deleted the data point that was like backtracking. So now it lets me create the core loss model. So once you have the core loss model in the material properties, you can hit OK and then hit OK and save your document. Yeah. Yeah. Yeah, I believe so. Let me check the data sheet. Oh yeah, so yeah, that does need to change. My mistake. So make sure you change the unit for the core loss to watts per kilogram. And the mass density, we'll find it in the data sheet. We just need to look for it. I think it's 7,650 kilograms per meter cubed. So make sure you input this for your core loss model. Core loss units, watts per kilogram. Mass density, 7,650 kilograms per meter per meter cubed. Frequency, 50 hertz if you chose the 50 hertz model. and unit Tesla, lamination thickness 0.27 millimeters. And we found all of this from the datasheet. So, saving the material. So, we need to set the core loss in the model as an excitation. It won't automatically simulate it. So if you right click like in space and go to assign excitation, then you can go to set core loss and it'll say defined in material. So it'll show you what materials you just defined the core loss for. So we're going to select all of these objects that we have a core loss model for. And the rest of these objects are copper and air, so we don't need a core loss model for that. And then hit OK and save that. Yeah, so right click out in space, or I believe you can right click excitations and go to, if you right click out in space, it'll be in assign excitation, and then go to set core loss and select all of the objects that have the defined in material checked on the right column. Yeah. 7,650. Okay. Now that we have the core loss model defined and set, the setup of this model should be okay, and the analysis here is different from the last model. I changed it to 2 electrical cycles because the core loss doesn't actually reach steady state until the 2nd electrical cycle. So I believe the frequency is at the base speed and the current is at the peak current we're deciding and peak torque. So now if you have this file in the student version, we're going to go to the electronic desktop version. Yeah, question? Yeah. It's basically just scaling it based on the frequency. Yeah. All right, I'm importing the file we were just working on. So now I'm going ahead and opening the file I imported to the virtual desktop on the full software. And if you expand the project and expand Maxwell 2D design and then expand analysis, go ahead and right click 2 electrical cycles and hit analyze. And now we're running a simulation of the motor running at the base speed at max torque, and it's running a core loss model, and it will also have a stranded loss model, which is going to give us our copper losses. So if you right click results, create transient report, rectangular plot, maybe we can first just look at the maybe I'll add this other lesson. You can create output variables. I never showed you this. So if you right-click results and go to output variables, you can create custom defined variables. So if I want a variable, I'm going to call it mean torque. Then I can just make the expression mean of, if you select torque, you can write, I believe it's called moving one dot torque. So mean of moving one dot torque, and then click add. It'll create this custom variable. And if you create the transient report, you can go to output variables and then look at the mean torque. And we're going to right click results again, create transient report rectangular plot. And now we're going to look at the losses. So I selected core loss. Here it's simulating the core losses. So right click results, create transient report rectangular plot, and then in category loss and then core loss. And we're also gonna create another report, and within the same category loss, we're gonna choose stranded loss, new report. And basically the stranded loss is the I squared R loss from the resistance of the resistors. I learned from other people, and I also watched some of, I'm trying to think of the name. I think it's like Calm Prog Expert. This channel is pretty good. So also you can take the average of a plot by right clicking the plot area and then clicking trace characteristics and then go to favorites and then click average. So the average I squared R loss is 969 watts. And going to the core loss model, we are going to create another report of the average core loss, but only over a certain period, which is going to be the second electrical cycle. So let's check what frequency we're running this at. So the base speed was at an electric frequency of 103.5 hertz. So calculator, 1 divided by 103.5. So the period is about 0.0096618 seconds. So I'm going to copy that to a few decimal places. So I'll rewrite it as well. So you don't have to memorize it right now. So right click results, create transient report, rectangular plot, and then go to loss, select core loss, and then we're going to click range function over here. And then if you go to oversweep time all, you can specify the range. So we're going to change the range from the end of the first electrical cycle to the end of the second electrical cycle. So I don't know if you can see that. It says 0.0096618 seconds. And then the max should be fine. And then if you hit OK, or click over here, hit OK, and then change this function to mean, new report, and then I'm going to use the marker to just check what the core loss is. So the core loss is actually really low for this motor, probably because it's running at a pretty low frequency. So the core loss is only about 65 watts. The stranded loss is about 970 watts. So I'm going to go back to the calculator. 970 plus 65. So the total losses approximately are about 1,000 watts.
Because you have laminated.
Laminated steel does reduce the core losses by a lot, because it eliminates, not completely eliminates, but reduces the eddy current losses. But there's still going to be hysteresis losses. But now we have the losses of the motor, and from the last lesson, we found out what the peak power of the motor was, and we're running it at this peak power point. So the power is 64,000 watts. So we're going to do 64 plus 1.035. So the input power is going to be 65.035 kilowatts. And the output power was about 64 kilowatts divided by 65.035. So the efficiency at the peak power point is actually really, really high. It's like 98.4% efficient at this peak power point. And if you run this efficiency simulation at multiple points, you can create sort of a heat map. And I did that with a different motor just to show you. Here is a 48 slot 10 pole IPM motor that I was working on, and I simulated over a range of different speeds and different torques while simulating the core loss model, and you can see the general trend is the losses increase as the torque increases, and the losses increase as the speed increases, but to varying degrees. So as the speed increases, the switching frequency of the electric signal, the electrical signal, is going to be increasing, and that increases core loss. And that's because of hysteresis. It increases the hysteresis and it increases the eddy currents. And the losses are also going to increase as you increase the torque because of the copper losses. Because as you increase the torque, you're increasing the current, therefore increasing the losses due to I squared times R, the resistance of each phase. So if you want to do this for your final project, it might be a cool graphic to put in your project. And what you need to submit for today, in terms of what you have to submit, I just want a screenshot of the core loss plot and a screenshot of the stranded loss plot, just to prove that you guys know how to find the losses of the motor through the simulation.